Hi class, this section is on polynomial functions of degree greater than 2. So, right here we have a polynomial of degree 0. That means it's just equal to a constant, and which is a horizontal line. When you have a polynomial of degree 1, that's going to look like a linear function, ax plus a sub 0, which is just a straight line with slope, a sub 1. Y-intercept, a sub 0. A polynomial of degree 2 is going to look like a quadratic, which means it has an x squared term, and that's going to have a vertical axis. So here we have two cubic functions because of the third power. They want us to sketch this on the same coordinate plane. So we have f of x, we should extend it out to include the g of x. So I will extend this out a bit and create a new column for g of x. Okay, we can choose any values we want for x, so I'm going to go ahead and choose negative 2, negative 1, 0, 1, and 2. So let's do the blue f in blue, and we'll do g in red. So if you substitute negative 2 into this function here, the f function, we're going to get f of negative 2 is 2 times negative 2 cubed plus 3. That's going to be negative 8 times 2 is negative 16 plus 3 is negative 13. And then if you substitute negative 1, you're going to get negative 2 plus 3, which is 1. If you substitute 0, you're just going to get 3. If you substitute 1, you're going to get 5. And if you substitute 2, you should get 19. All right, we'll do the same thing for g. G of negative 2 is going to be negative 2 times negative 2 cubed plus 3. That's going to be positive 16 plus 3, which is 19. And if you plug in the rest of the numbers, the rest of the x values into the g function, you should get 5 for the next one, 3. That is going to be 1, and that is going to be negative 13. So now we can plot these points. Let's graph the f function first. The first ordered pair would be negative 2 comma negative 13. All right, we're going to have to go by 5, 10, 15, 12, 1, 2, 3, 4, 5. We can go by 4s. So let's go by 4s. So this would be 4, 8, 12, 16, 20. All right, so when x is negative 2, we have negative 13. So that's going to be negative 4, negative 8, negative 12, negative 16, negative 20. So negative 2, negative 13 would be down here somewhere. And then we have negative 1, positive 1. We have 0, 3, 1, 5, and 2, 19. And so there's our cubic graph. And that is f of x. And if you graph g, it's going to look very similar. It's just going to be reflected over the y-axis, as you will see. Negative 2, 19 would be way up here. Negative 1, 5 would be about right here. 0, 3 would be at the same spot the other one was. 1, 5 would be, 1, 1. Wait, where am I? 0, 3, 1, 1 would be down here. And 2, 19. 2, negative 1 will be down here. All right, I think I messed up on one of these. Let me try that again. Negative 2, 19, negative 1, 5, 0, 3, 1, 1, and 2, negative 1. All right. So there we have it. All right. And now we can move on to the next problem. So the intermediate value theorem for polynomial functions, if f is a polynomial function and f of a does not equal f of b and a is less than b, then f takes on every value between f of a and f of b in the interval a to b. So let's use the intermediate value theorem to show that this function has a 0 between 2 and 3. So 2 and 3 are going to be our a's and b's, our a and b respectively. So let a be 2 and b be 3. And we need to ensure that a is less than b, which it is. A is less than b. And let's find out what f of a is. F of 2 and f of 3. If you substitute 2 into this function, you should get negative 2 to the 4th plus 3, 2 cubed, minus 2 times 2 plus 1. And same thing with f of 3, you do the same thing. Let's see what we end up with. Using our calculators, we should get I'm getting 5 for this one, and for the bottom one, I'm getting negative 5. All right, so what the intermediate value theorem is saying, well, let's draw the picture so we can get a visual of what's happening here. So we have 1, 2, 3. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All right, so at f of 2, the function value is 5, and at f of 3, the function value is negative 5. So what the intermediate value theorem says, it says that f takes on every value between that. So if f takes on every value between 5 and negative 5, that means it must cross the x-axis somewhere between 2 and 3. And so that's what it's saying. It's saying that f has to take on every value between f of 2 and f of 3. So therefore, there must be a 0 somewhere between 2 and 3. That's what this theorem says. All right, so we can write that in words. Let's say, by the intermediate value theorem, I'm going to abbreviate, there is a 0 between, I'll just say in the interval, two, 3. And that's it. All right, for the next example, they're asking us, they say let f of x equal this function, find all the values of x such that the function is positive, and all the values of x such that the function is negative, and then sketch the graph. So the way we should start this off is by finding the zeros, so that's what they're asking us to do. So we set the function equal to 0 and solve. Since we have a 4-term polynomial, we want to try factoring by grouping, which we should be able to do. If you factor out the first GCF, you will get x squared parentheses x plus 1. And if you factor out the GCF from the second group of numbers, that's going to be negative 5. And you'd be left with x plus 1. You can verify that by distributing. You'll get negative 5x minus 5. And we know that we're doing this correctly because these two binomials are equal. So now we can take out that binomial. If you take out the x plus 1 binomial, factor it out to the front, you will be left with x squared minus 5. And now we can solve these two factors by setting them equal to 0. So this 0 will be negative 1, and this will be x squared equals 5, which means that x equals plus or minus radical 5. So there are 3 zeros here. 1, 2, 3. So we can graph those first. Let's start off with that. So negative 1 would be here. Radical 5 is approximately 2.2. So that would be positive 2.2 would be about right here. And negative 2.2 would be about right here. All right, so we have our 1, 2, 3 zeros. All right, and now we need to select any point in this interval to test to see if the function should be above the x-axis or below, positive or negative. So I'm going to test a few values here. Let's test negative 3 would work. We need to test the number that's in between these two zeros. So I'm going to go ahead and test negative 2. Negative 2 is between. And then for that other one, 0 would work. And for the last one, 1, 2, 3 would work. So now we have a number that's to the left, in between those 2 points, in between those 2 points, and to the right. So we plug it into either the factored version or the original. I'm going to plug it into the factored version. So if we plug in negative 3, we're going to have negative 3 plus 1 is negative 2 times, if you plug in negative 3 here, that's going to be 9 minus 5 is 4. So that's going to be a negative times a positive, which is a negative. So therefore, the function will be negative. I'm going to create these little columns. So we know that the function is going to be on the bottom for the first interval. Now we have to check between these 2 points. So we plug in negative 2. Negative 2 plus 1 is negative 1. And negative 2 squared is 4. 4 take away 5 is negative 1. So we have a negative times a negative, which is a positive. And then between 0, I recommend just plugging it into the original function. So 0, 0, 0, you're going to get negative 5. So it's going to be negative again. And for 3, if you plug in 3, this is 3 plus 1 is a positive. And 3 squared minus 5 is a positive. So you're going to end up with a positive here. So the graph is going to start at the negative, and it's going to hit this point, but it's going to stay negative. Oh, I'm sorry. No, it goes positive. My mistake. It's going to go negative to positive, and then back to negative, and then back to positive. And that's because it's going to be negative here, and then it is positive here, and then it's negative again, and then it's positive. So that's how you would graph or sketch the graph. And now we can determine the intervals on which the function is positive and the intervals on which the function is negative. Let's start with the positive. The function is positive here and here. So that would be from this 0 to this 0. So let's write that here. Positive, or I'll just write it in a more mathematical way. F of x is greater than 0 on the interval from negative radical 5 to negative 1, union from positive radical 5 to infinity. So that would be this interval for this one, and this interval for this part of the function. All right, and then it's going to be negative or less than 0 here and here. So from negative infinity to negative radical 5, union from negative 1 to positive radical 5. So negative 1 to positive radical 5. And that is the intervals on which it's negative and positive. Let me write this a little nicer. There we go. Okay, so that would do it. Okay. Let's try the next problem. This is the same directions. The only thing is different is the function itself. So let's see how we can find the zeros of this function. We set it equal to 0, same as before. So since this is a trinomial, we want to try to factor this by using the diamond method. So this would be 8 and -6, -4, -2 would work. So this is factorable. X squared times x squared is what gives us the x to the 4th power. And now we need -4 and -2. This one can be factored further. X plus 2x minus 2, that's a difference of 2 squares. This one cannot be factored further. And now we can set all of these individual factors equal to 0 to solve. This will be -2. This will be +2, and this will be plus minus radical 2, which is approximately 1.4. So let's graph those 4 points. So -2 would be here. -1.4 is about right here. +2 would be here. +1.4 would be about right there. All right, and just same as before, we need to pick a point in this interval, this interval, this interval, this interval, and this interval. So we're going to test a few points here. I'm going to choose -3 for the left. Between these 2 points, I will choose -1.5. Between 0 would work for the other one, and then +1.5, and finally +3. So there's quite a few points to test here. All right, so for the first one, -3, if you plug in -3 here, that's going to be 9 minus 4 is positive, and 9 minus 2 is positive, so you're going to have a positive. All right, for -1.5, -1.5 squared is 2.25, so this is going to be negative, and this is going to be positive. So negative times a positive is a negative. For 0, I always plug it into the original. That's going to be +8, so that's positive. For 1.5, it's going to be the same as this one. It's going to be negative, because when you square a negative, it's going to be the same result as squaring a positive. And similarly, this one's going to have the same result as that one. So it's going to be positive. So it looks like the graph goes positive to negative, positive to negative, back to positive. So it's going to have that W. It's going to look like a W. And that's our function. And now we can state the intervals on which the function is positive. So that would be from -infinity to, from -infinity to that point to the left, which was -2. So -infinity to -2. And then also from negative radical 2 to positive radical 2. And then also from 2 to infinity. So we got this interval, and this interval. And then the function is negative here and here. So that would be, those two intervals would be written as -2 to negative radical 2 union radical 2 to 2. And that's the final answer. Notice that the intervals are always open parentheses for all of these. You would never use square brackets for intervals of positive and negative functions.